good afternoon. Welcome to a wonderful Wednesday of calculus. Now, to make sure you guys are actually awake and with it here, I have a few mathematical riddles for you before we get started. So, all of your answers are, of course, mathematical terms. First riddle. What do you call an insect that's not feeling well? The answer is a seek ant. Get it? Seek ant. Your next riddle. What do you call a parrot who should go on a diet? The correct answer is a polynomial. Riddle number 3. What do you call a mermaid's undergarment? Correct answer is an algebra. How's about what math is discussed between seabirds? This is a toughie. The correct answer is integral calculus. And last but not least, what does a mathematician read every Sunday morning? And of course, the answer has to be the conic section. Now, I know you love diabolic jokes, and so now we're ready to get down to the serious stuff. As you can see here on the first page, I have described to you what wonderfully fun, exciting things you're going to get to do in this chapter. This is the chapter I think of as your special derivatives. We learned the basics last time. We know how to do derivatives of standard polynomial functions, rational functions, quantities to a power, anything we can handle with product, quotient, and chain rule. Well, now we're going to deal with some different items as well. There's three primary topics in this chapter we're going to hit. Today's topic is what we call implicit differentiation, and I'll get back to more on that in a second. In next class, we're going to be dealing with the derivatives of logarithms and also fun, exciting exponential functions. And those exponential functions can not only be the traditional a number to a variable, but it can also be e to a quantity power, or even more exciting, something you've never done before, a variable raised to a variable power. Woo! Sounds exciting. We'll also be learning the derivatives of the inverse trig functions and relating that to Romeo and Juliet. And last but not least, you get to learn L'Hopital's rule from a French mathematician by the name of L'Hopital. And that pertains to finding some limits of functions we could not do with what we knew from the limit tree. It takes derivatives to find these limits, and now we will be able to do it with L'Hopital's rule. All fun and exciting stuff for you to look forward to. As I told you the other day, this is not an easy chapter, so be prepared. So, however, today we're talking implicit differentiation. And the key to implicit differentiation is actually understanding what's the difference between explicit differentiation and implicit differentiation. Yes, it's vocab time. I don't think you've had these words on your vocab for Mrs. Hecht, but if you haven't, maybe you will. So, I'm sure you all have seen the word explicit before. I regularly see that word show up when my 4th grader is searching for rap songs on iTunes. So I know you have some concept of explicit, but dictionary definition-wise, explicit is something that's fully revealed or expressed, has no vagueness or ambiguity. In other words, there's no question as to what its meaning is. Mathematically, an explicit function is one that's defined in terms of y equals 3x squared plus 7x minus 4. That explicitly defines y in terms of x's. You know exactly what y is in terms of x's. There's no doubt about what y equals. Okay. On the other hand, you can have implicit expressions. And the word implicit means that something's capable of being understood from something else, though not expressed. It's something that's implied. You don't have it clearly spelled out for you. It's not clearly defined. In our case, mathematically, it means that we're not going to clearly know what y equals in terms of x. An implicit expression would look something like this. Y squared plus 3xy plus 7 equals 2 minus 5y. That's an implicit function. You don't clearly know that what y equals in terms of x. And algebraically, this would be quite difficult to solve and to even isolate y if we wanted to. So we need a way to find, in our case, we want to find a derivative here, but we don't have y spelled out for us as to what it equals in terms of x. Okay. We are going to play a little pretend game here for a few minutes so I can get across why implicit differentiation works the way it does. Okay. I want to point out, this one is defined explicitly, the y equals 3x squared plus 7x minus 4. If I say to you, find me dy over dx, or in other words, find its derivative, you guys can do that. That's an easy little power rule. We know it's going to come out to be 6x plus 7. I cannot come over here to the implicit function and define it and say, here's what dy over dx is. Since I can't isolate y, I can't come up with its derivative either. So we're going to play our little pretend game with this function. Y squared plus x cubed plus y cubed equals 5. Now, why is this an implicit function? And I'm sure you all just said, because you can't define y in terms of x. We can't just go solve for y and say what y equals in terms of x. So we are going to we're going to play a pretend game. We're going to pretend that y, in this case, is this what we defined up here. We're going to pretend that y is really this little trinomial, 3x squared plus 7x minus 4. So I am going to insert that little function in place of every y I see here. This is not how you will actually work your problems. We're going to get to a shortcut once we figure this out. So I would have that little function squared plus x cubed plus, here's another y, so I'm going to pretend that y is also 3x squared plus 7x minus 4. And this time it's to third power. And that's supposed to equal 5. Okay, what we want to do is we want to find the derivative of both sides of this equation. That's also a little unusual, but in implicit differentiation, you do the derivative of both sides. So if I said to you, find me the derivative of this first piece, this quantity to the second power, hopefully you're all screaming, it's a chain rule! So we need to do a chain rule on it. So I'm going to take my power, put it out front, and of course I'm not going to change the quantity on the inside, and it's now the what power? And yes, the first is correct. Am I done with this chain rule? Answer, of course, is no, we haven't done the derivative of the inside. So I now need to times it by the derivative of the inside. Well, the derivative of the inside is, of course, 6x plus 7. No big deal. What we had already noted up here, dy over dx is 6x plus 7. Okay, moving on to the next piece. The next piece is just a plain old x cubed. It's not a quantity to a power, so we can just do a regular old power rule on it and get 3x squared. Then, this third piece is once again a quantity with a power on it, so I'm going to have to do another chain rule. So I'm going to put the 3 out front. I'm going to write the whole quantity down, and now have it to the second power. I have to times by the derivative of the inside again. So I'm going to have times another 6x plus 7, the derivative inside, and that will take care of that piece. Last, I need to do the derivative of what it's equal to, and the derivative of plain old 5 is 0. Okay, now once again, you are not going to have to do it this way. We're going to find an easier method in a minute, because we're going to now relate this back to our original functions we had written up here. You'll notice that I'm going to take now and replace all the quantities, all the 3x squared plus 7x minus 4s. That's what we defined up here at the top as what y is equal to. So I'm going to use that expression and say, okay, this whole trinomial is really just a y. So I really have 2y there to the first power times the 6x plus 7 is the derivative. It's what we defined up here to be dy over dx. So I am going to change that 6x plus 7 into dy over dx. Okay, then I still have plus 3x squared plus 3. Once again, the trinomial is y, so I have 3y squared here, times 6x plus 7 was the derivative, and that is equal to 0. We can now proceed from there to actually solve for dy over dx. So first, however, I want you to make the connection into how did I get from the original problem I had up here down to this step I just got to here. How did I get that to happen? I want to skip those two steps in the middle. I want to figure out how can I get from step 1 to step 4 without having to do all that work in the middle. Because in reality, we really are pretending. We don't know that 3x squared plus 7x minus 4 is what y is equal to. So if you notice, how did I get from y squared to a 2y times dy over dx? Well, hopefully you're noticing that, hey, derivative of y squared, if you do the power rule, is just 2y. So all I did is the derivative of y squared got 2y. But because I didn't really know what function y was, I'm chain ruling it and saying, oh, if I knew what y was, I would do its derivative. So I have to tack this dy over dx on the end of it. Okay. Then I have the plus 3x squared. Well, that came from doing the derivative of x cubed. That was not a y variable, that was an x variable, so everything's okay. I just did your normal power rule. Didn't have to do anything special when I did the derivative of an x. But now, y cubed, when I do its derivative of y cubed is 3y squared. So I got 3y squared down here. But because it was a y, and I didn't know what its inside function was, I have to say I'm going to take it times dy over dx, so that I'm actually doing the chain rule on it. And then, of course, derivative of 5 was 0. That did not involve a y, so I didn't have to do anything special. So you can see there, for right now, whenever we do the derivative of a y, we have to add the extra dy over dx on it because we are actually doing a chain rule.